What if the story of creation, our story, is missing its very first chapter? We have long believed we knew the origin of black holes, those cosmic behemoths of infinite density. They are born, we thought, from the spectacular death of colossal stars, their cores collapsing under an impossible gravitational strain. They are the tombstones of suns, the final act in a grand celestial drama. But this tidy narrative, this clean line from life to death, to singularity, may be profoundly incomplete. What if the universe didn't wait for stars to die to forge its monsters? What if in the very first incandescent second of its existence, amidst a firestorm of creation that defies all analogy, the cosmos gave birth to black holes directly from the raw seething energy of the Big Bang itself? Imagine a darkness older than the first star, a gravity that predates the first galaxy. These are not the children of stellar collapse. They are something else entirely. Phantoms from a time before time as we know it, relics forged in the crucible of the universe's most violent instant. We call them primordial black holes, and they represent one of the most tantalizing and unsettling possibilities in all of cosmology. Their existence, if confirmed, would not just add a new chapter to our story. It would force us to rewrite the entire book from the first page to the last. It would mean that the universe has been haunted from its very beginning, seeded with a population of invisible ancient objects that could hold the key to our greatest cosmic mysteries. To understand how such an audacious idea is even possible, you must cast your mind back beyond the swirling nebulae, beyond the first glimmer of starlight, beyond the formation of the first atom. We must travel to the edge of comprehension itself, to a moment when all the matter and energy of the observable universe, every galaxy, every star, every planet, every one of us, was compressed into a space smaller than a single grain of sand. This is the universe at a mere fraction of a second old. It is not a place of empty space and distant lights. It is a cauldron of pure, unimaginable energy. A perfect, uniform, terrifyingly hot soup of fundamental particles, a quark-gluon plasma churning at trillions of degrees. In this primordial state, the familiar laws of physics were still fluid, the four fundamental forces of nature perhaps united as one. Space-time itself was a turbulent, frothing ocean, expanding at a rate so extreme it beggars belief. This was the era of cosmic inflation, a hyper-accelerated expansion that stretched the universe from the subatomic to the astronomical in less than the blink of an eye. It was an epoch of incomprehensible violence and beautiful, terrifying simplicity. Within this uniformity, however, quantum mechanics guarantees there were impossibly tiny fleeting fluctuations, microscopic ripples in the otherwise smooth fabric of reality, quantum jitters in the density of the primordial soup. For the most part, these ripples were insignificant, smoothed out by the universe's relentless expansion. But what if some were not? What if in a region of space-time infinitesimally small, a quantum fluctuation created a pocket of energy that was just for a moment catastrophically dense, a region so massively overdense, so gravitationally potent, that the explosive outward force of the Big Bang was not enough to tear it apart? In that fleeting instant, the rules of destiny would change for that tiny patch of the cosmos. Instead of expanding with the rest of the universe, it would do the opposite. It would collapse, instantly, violently, and completely. It would collapse in on itself, crushing energy into matter and matter into a point of infinite density. It would become a singularity. It would become a black hole. This was the revolutionary insight proposed decades ago by physicists like Yakov Zeldovich and Stephen Hawking. They realized that the extreme conditions of the early universe were a perfect forge for black holes requiring no dead star, no stellar core, no gradual process of collapse. These primordial black holes would have been born in a flashfully formed singularities birthed from the pure chaos of creation. They wouldn't be limited to the large masses of their stellar cousins. Some could be as massive as 1,000 suns, while others might be no more massive than a mountain or a car or even a single asteroid compressed into a volume smaller than an atomic nucleus. They would be a new class of object, a cosmic species unto themselves, scattered like dark seeds throughout the infinite universe. Once formed, they would become cosmic fossils, silent witnesses to the universe's birth. While the primordial plasma around them cooled and thinned, eventually forming hydrogen and helium atoms, these pockets of infinite gravity would simply persist. They would drift through the cosmos as it expanded and evolved unaffected by the maelstrom of light and matter. They were the universe's firstborn objects, yet they played no part in the brilliant drama of the first stars. They were the silent audience. As the cosmos slowly transitioned from a featureless glowing fog into the transparent star-dusted darkness, we know today these primordial black holes would have been there, invisible, ancient and waiting. And here the story moves from a fascinating theoretical possibility to something far more profound, touching upon the single greatest enigma in modern astronomy. As we gaze out into the cosmos, we see a profound discrepancy, a gravitational ghost in the machine. We see galaxies spinning faster than they should, their stars held in a gravitational grip far too strong for the visible matter they contain. We see clusters of galaxies bound together by an unseen cosmic web, a scaffold of immense mass that we simply cannot detect. This invisible substance, this gravitational glue holding the universe together, is what we call dark matter. It outweighs all the stars, gas and dust in the cosmos by a factor of more than 5 to 1. We know it is there. We can map its influence, yet we have no idea what it is. For decades we have searched for exotic subatomic particles that might constitute this dark matter, building vast sensitive detectors deep underground, hoping to catch a fleeting glimpse of a WIMP axion or some other hypothetical particle. But all of these searches have so far come up empty. The ghost remains a ghost. This long and fruitless search has forced scientists to reconsider, to look for answers not in the realm of the impossibly small, but in the realm of the impossibly dense. What if dark matter isn't a new particle at all? What if the missing mass isn't a diffuse cloud of exotic stuff, but is instead composed of discrete, compact, invisible objects? What if the universe is filled with a vast swarming population of primordial black holes? The idea is as elegant as it is radical. Primordial black holes perfectly fit the description of dark matter. They are dark, interacting with their surroundings almost exclusively through gravity. They are massive, each one containing a concentrated lump of the universe's missing mass. And they are primordial, formed before the synthesis of the light elements, meaning they would not disrupt the delicate cosmic accounting that so accurately predicts the abundance of hydrogen and helium we observe today. They could be the solution hiding in plain sight, a population of cosmic relics that collectively masquerade as a mysterious unidentified substance. The gravitational scaffolding holding you, your planet, and your entire galaxy together might not be a cloud of unknown particles, but a swarm of the oldest black holes in existence. If this is true, their influence would be written into the very fabric of the cosmos. They would be more than just passive relics. They would be active architects of cosmic structure. In the early universe, long before the first stars could ignite, these primordial black holes would have acted as gravitational anchors. They would be the seeds of density, the gravitational high ground, around which the first wisps of gas could begin to gather. A cloud of hydrogen drifting through the void would feel the pull of one of these ancient objects, its immense gravity acting as a cosmic shepherd, gathering the diffuse matter into a concentrated fold. Over millions of years, these small pools of gas, anchored by their dark primordial cores, would grow, attracting more and more material until they reached a critical mass. Within their centres, pressures would build, temperatures would soar, and eventually the fires of nuclear fusion would ignite. The first stars would be born not in isolation but clustered around these invisible gravitational cores. This process would cascade upwards. Stars would gather into the first star clusters. Star clusters would merge to form the first dwarf galaxies, and these dwarf galaxies, each one perhaps silently governed by a central primordial black hole, would themselves be drawn together along the vast filaments of the cosmic web, coalescing to form the grand spiral and elliptical galaxies we see today. Even the supermassive black holes that reside at the heart of nearly every major galaxy, including our own Milky Way, could find their origin story here. Perhaps they didn't grow slowly over billions of years, but were instead born from the merger of these smaller ancient seeds that were there from the very beginning. In this scenario, primordial black holes are not just a solution to the dark matter problem. They are the missing link in our understanding of cosmic evolution. They are the agents of creation, the catalysts that transformed the smooth, nearly uniform universe of the post-Big Bang era into the rich, complex and structured cosmos we inhabit. Without them, the formation of galaxies might have taken far longer, or perhaps not happened in the same way at all. We might be living in a universe whose fundamental architecture was laid down in the first second of time by a population of invisible primordial singularities. But how could we ever prove it? How do you find a ghost? These objects are by their very nature the masters of stealth. A primordial black hole with the mass of a planet would be smaller than a marble. One with the mass of our sun would be only a few kilometers across. They emit no light. They reflect no light. They are perfect pockets of darkness adrift in the cosmic ocean. Finding them seems an impossible task, a search for the tiniest of needles in an infinite haystack. Yet we are on the verge of a revolution. We are developing tools and techniques that allow us to listen for the universe's most subtle whispers, to search for the faintest of gravitational echoes left by these phantoms as they move through space-time. We can look for the way their immense gravity bends the light of distant stars, a phenomenon known as gravitational lensing. As a primordial black hole passes in front of a background star, its gravity would act like a cosmic magnifying glass briefly, and characteristically brightening the star's light, a fleeting, telltale sign of a dark object passing by. We can also listen for the echoes of their cataclysmic mergers. When two black holes, primordial or otherwise, spiral into each other and combine, they unleash a storm in the fabric of space-time itself, gravitational waves. Our new observatories are now sensitive enough to detect these ripples, and the specific signature of a primordial black hole merger would be distinct, a unique gravitational song that could betray their ancient origins. And then there is the most exotic possibility of all, a prediction that comes directly from Stephen Hawking himself. Black holes, he theorized, are not entirely black. Due to quantum effects near their event horizons, they should slowly leak a faint trickle of radiation back out into the space, a phenomenon now known as Hawking radiation. For massive star-sized black holes, this process is infinitesimally slow, taking longer than the current age of the universe to evaporate. But for the very smallest primordial black holes, those born with the mass of a large mountain or less, this evaporation would be much faster. As they reach the end of their lives, this trickle would become a torrent, culminating in a final explosive flash of high-energy gamma rays. If we could detect such a flash, a burst of energy from a point in space, with no star, no galaxy, no other explanation, we would have captured the death cry of an object born in the Big Bang. We would be witnessing the final spectacular end of a 14 billion-year journey. The quest for primordial black holes is therefore a journey into the heart of our own cosmic ignorance. It is an investigation that connects the largest structures in the universe with the most fundamental quantum laws. It challenges our assumptions about the nature of matter, the formation of galaxies, and the ultimate inventory of the cosmos. These objects represent a tantalizing bridge between the universe we can see and the vast dark sector we cannot. They are a potential solution to multiple seemingly disconnected cosmic puzzles, a single key that could unlock several of modern science's most heavily guarded doors. So we stand at a precipice of discovery, looking back across the abyss of 14 billion years. The evidence for these objects is circumstantial, tantalizing, but not yet conclusive. They remain ghosts in our theories, spectres in our data. But the search is on, driven by the profound implications of what we might find. Because if they are out there, if the universe is indeed filled with these relics of creation, it means that the darkness between the stars is not empty. It is filled with the oldest objects in existence. It means that the story of our universe is fundamentally a story of black holes, not just as the endpoints of cosmic evolution, but as its very beginning. Our journey through this documentary is to chase these ghosts, to follow the faint clues they may have left behind, and to ask one of the most fundamental questions we can pose: did the universe forge its own destiny in the dark long before it ever created the light? What if the most profound monsters in the universe were not born from the spectacular deaths of stars, but were instead ghosts from its very first breath? What if there are black holes haunting the cosmos that are older than the first atoms, older than the first light? These are not the familiar gravitational titans we think we know. They are something else entirely, a primordial echo of creation itself, hiding in plain sight. To find them, we must first unlearn what we think we know about gravity's ultimate triumph. We must travel back not just through space, but through the deepest corridors of time to an era so violent and alien it almost defies imagination. Our journey begins not in the sky, but on the page with a revolution that redefined the very stage on which the cosmos plays out. Before Albert Einstein, we saw the universe as a grand cosmic clockwork, a vast static emptiness through which planets and stars moved, pulled by an invisible instantaneous force called gravity. It was predictable, orderly, and fundamentally simple. But in 1915, Einstein shattered that clockwork forever. He revealed that space is not empty, and time is not absolute. He gave us the astonishing vision of space-time, a single, unified, four-dimensional fabric. And this fabric, he proposed, was not a passive backdrop. It was an active participant in the cosmic drama. Matter and energy tell space-time how to curve, and the curvature of space-time tells matter and energy how to move. It's a concept so profound it feels like poetry. A planet doesn't orbit the sun because of a mysterious pull. It follows the straightest possible path through space that has been warped and dimpled by the sun's immense mass. It is perpetually falling into a valley in reality, but moving just fast enough to constantly miss. This elegant dance between mass and geometry rewrote our understanding of the heavens, but within its beautiful equations, Einstein had unknowingly hidden a monster. His theory predicted that if you could gather enough matter into a small enough space, the curvature of space-time would become infinitely steep. Not just a gentle valley, but a bottomless pit, a point from which the fabric of reality itself could not recover. At this location, gravity would cease to be a mere force directing traffic. It would become an unstoppable cataclysm, a runaway collapse from which nothing, not even light, the fastest thing in existence, could escape. For decades, this was considered a mathematical absurdity, a flaw in the equations that nature would surely never allow, a physical impossibility. The universe, we believed, had safeguards. It was too elegant, too orderly to produce such a singularity, such a complete and utter breakdown of physics. But the universe, it turns out, is far more violent and creative than we had ever imagined. The safeguards we discovered can fail. We found the engine for creating these monsters in the hearts of the most colossal stars, the blue giants that burn with a fury 1,000,000 times that of our own sun. For millions of years, these stellar titans are the universe's great alchemists, magnificent nuclear forges where the light elements born in the Big Bang are crushed into the heavier materials that make up planets, and even you. Hydrogen fuses into helium, helium into carbon, and on up the periodic table. This constant outward exploding energy from fusion provides the pressure that holds the star up, fighting a relentless lifelong battle against the inward crush of its own colossal gravity. It is a titanic struggle, a balancing act on a knife's edge that defines the star's entire existence. But this battle cannot last forever. Every star is born with a finite amount of fuel. When a truly massive star, one more than 20 times the mass of our Sun, exhausts its nuclear reserves, this delicate equilibrium is shattered in an instant. The outward pushing furnace in its core sputters and dies. In that moment, gravity, the patient ever-present force, finally wins, and its victory is absolute. With no outward pressure to support it, the star's core, a sphere of iron and nickel containing more mass than our entire Sun, collapses in upon itself. It implodes at 1/4 of the speed of light. The collapse is so catastrophic, so unimaginably violent, that it triggers the most powerful explosion we know of a supernova. The star's outer layers are blasted into space in a brilliant, fleeting blaze that can outshine an entire galaxy of 100 billion stars. This celestial death cry seeds the cosmos with the elements necessary for new stars, new planets, and new life. It is a beautiful cyclical story of cosmic death and rebirth. But left behind in the heart of that fading ethereal nebula of gas and dust is the monster from Einstein's equations. The collapsed core, now crushed beyond all comprehension, continues to shrink. It smashes past the density of an atomic nucleus, past every known state of matter, until it is compressed into a region of zero volume and infinite density. A singularity. It has punched a hole in the very fabric of space-time. A black hole is born. This has become our standard model, the canonical story of how these gravitational phantoms are made. It requires a specific set of circumstances, a giant star, the exhaustion of its fuel, and a spectacular explosive death. For half a century we believed this was the only way. We looked out at the cosmos and saw these stellar mass black holes, the cinders of dead giants, and assumed they were all cast from the same mould. We'd convinced ourselves that to make a black hole, you first needed to make a star. This assumption, however, rested on a subtle but profound bias. It was based on the conditions of the universe as we see it today. A vast, cold and mostly empty place where the only factories dense enough to forge a black hole are the cores of dying stars. But what if we were only looking at one chapter in a much longer, much stranger cosmic story? What if there was another way? A way that required no stars, no fusion, no supernovas. A path to infinite collapse that existed only in the universe's most extreme and distant past. This was the revolutionary question that began to percolate in the minds of a new generation of theorists in the late 1960s and early 1970s. They were looking at the cosmos not just through telescopes, but through the lens of pure mathematics guided by the still unfolding implications of Einstein's relativity. Among them was a brilliant young physicist at Cambridge University, a man whose mind was already soaring to the farthest reaches of theoretical possibility even as his body was beginning to fail him. Stephen Hawking, alongside his colleague Bernard Carr, would propose an idea so radical it would forever change our view of what a black hole could be. They looked past the modern, placid universe of today and peered into the inferno of its birth. They argued that the conditions in the moments immediately following the Big Bang were so utterly alien, so much more extreme than the core of any star, that black holes could have been forged directly from the raw energy and chaos of creation itself. They didn't need a star to die. They just needed the universe to be born. These would not be stellar remnants. They would be something far more fundamental, primordial. To understand their breathtaking hypothesis, you have to perform an act of immense imagination. You must forget the tranquil darkness of the night sky dotted with distant lonely stars. You must erase the galaxies, the planets, the very atoms in your body. We have to journey back 13.8 billion years to the first fraction of the first second of time. Here, the entire observable universe, all the energy, all the matter, all the potential for everything that would ever exist was compressed into a space smaller than a grain of sand. This was not a universe of structure or form. It was a seething, incandescent cauldron of pure energy, a perfect uniform plasma hotter and denser than anything we can truly conceive. The fundamental forces of nature were merged into a single unified superforce. The concepts of space and time themselves were just beginning to unfurl. In this primordial soup there were no clumps of matter. The universe was astonishingly, almost perfectly smooth. The density was virtually identical from one point to the next. It was this very smoothness that had long puzzled cosmologists. If the universe started out perfectly uniform, how did it ever develop the structures we see today? How did the galaxies, stars and planets ever form? The answer we now believe lies in an event that took place in that first sliver of a second cosmic inflation. For a fleeting instant, the universe underwent a period of hyper-accelerated expansion, swelling from a subatomic size to something vaster than a galaxy, faster than the speed of light itself. This explosive growth ironed out any large-scale wrinkles, making the universe incredibly flat and uniform on the grandest scales just as we observe. But it also did something else, something critically important. It took the microscopic, ghostly world of quantum mechanics and blew it up to astrophysical proportions. At the quantum level, the universe is not smooth. It is a roiling, frothy sea of uncertainty. Particles and energy can pop in and out of existence in a phenomenon known as quantum fluctuation. In the tiny pre-inflationary universe, these fluctuations were happening constantly, creating minuscule transient variations in the energy density of the primordial soup. They were infinitesimal ripples on a microscopic pond. But then inflation hit. As the universe expanded at this unbelievable rate, these tiny quantum ripples were stretched, magnified and frozen into the very fabric of space-time. Microscopic flickers of energy were suddenly transformed into vast continent-sized regions of slightly higher or lower density. The seeds of all future structure had been sown. Most of these density variations were gentle, like subtle hills and shallow valleys in the cosmic energy field. Over hundreds of millions of years, gravity would patiently work on these overdense regions, pulling in more and more material until they eventually blossomed into the first galaxies and stars. This is our grand story of cosmic evolution. But Hawking and Carr asked a provocative question. What if not all of these primordial ripples were so gentle, the quantum world is governed by chance? While most fluctuations would be small, was it not inevitable that some by pure random happenstance would be exceptionally large? What if in some places the initial density fluctuation was not just a gentle hill, but a towering, impossibly steep mountain? In the turbulent chaos of the early universe, an era of unimaginable pressures and energies, could a region become so fantastically dense that it would simply collapse under its own gravity, right then and there? It would bypass the entire life cycle of a star. It wouldn't need to wait for nuclear fusion to begin and end. The sheer density of the newborn universe itself would be enough. The overdense pocket of plasma and energy would not become a galaxy. It would become a black hole, born not in fire but from pressure. Not in a supernova, but in the silent, instantaneous collapse of a patch of the baby universe itself. This mechanism shatters our established framework for making black holes. The stellar mass black holes we observe are constrained by the physics of stars. You need a star of at least 20 solar masses to create one, and even the most massive stars top out at a few hundred solar masses. This gives you a very narrow range of possible sizes for the resulting black holes. But primordial black holes, or PBHs, would have no such constraints. Their size would depend entirely on the scale of the initial density fluctuation that created them. A small but incredibly dense fluctuation in the first fractions of a second could have collapsed to form a black hole with the mass of a large mountain, yet smaller in physical size than a single proton. A larger fluctuation happening a moment later when the universe had expanded slightly might have created a PBH with the mass of our moon or even the Earth. Some could be as massive as a dwarf planet or 1,000 suns all formed before the first star ever ignited. Suddenly, the cosmic bestiary had exploded with new possibilities. The universe might be populated by an entire unseen family of black holes, spanning a breathtaking spectrum of masses. On one end, you have subatomic black holes, quantum ghosts born in the ultimate high-energy particle physics experiment that was the Big Bang. On the other, you could have colossal black holes thousands of times more massive than our Sun, which could have acted as the gravitational seeds around which the first galaxies coalesced. They would not be the children of the stars, they would be their ancestors. This theory paints a picture of a fundamentally different kind of universe. Not one where black holes are rare, exotic endpoints of stellar evolution, but one where they are a common, perhaps even essential component of the cosmic fabric, forged as a natural byproduct of creation. They would be the oldest objects in existence, cosmic fossils preserved since the first moments of time. They would have witnessed the entire history of the universe unfold around them, silent and invisible. They would be made not of the compressed matter of a dead star, but of the very stuff of the Big Bang itself, the raw primordial energy plasma locked away from the rest of space-time for eternity. They are a direct physical relic of the universe's most mysterious and inaccessible era, a time capsule from the dawn of everything. If they exist, they are not just a curiosity. They are a message from the past, carrying secrets about the nature of inflation, the laws of quantum gravity and the very origin of structure in the cosmos. Their presence would reshape our entire cosmological model, forcing us to reconsider the inventory of what the universe is truly made of. And yet, this remains one of the greatest and most tantalizing ideas in all of science. It is a ghost story, a tale of invisible monsters born at the beginning of time. For all its theoretical elegance, for all its profound implications, we are left with a single overwhelming question. The theory is beautiful, the mathematics compelling. But after 50 years of searching, after peering into the darkness with our most powerful instruments, is there any proof? If the universe truly forged these primordial relics in its fiery birth, where are they now? How could we possibly hope to find these ancient dark wanderers adrift in the 13.8 billion years of cosmic history that separates us from their violent creation? The hunt for these ghosts from the dawn of time is one of the great scientific detective stories of our age, a search that pushes the boundaries of observation and ingenuity. For if we can find even one, it will not just confirm a theory, it will give us a direct window into the moment of creation itself. And so this extraordinary concept, a black hole forged not in the death of a star, but in the very first infernal second of time itself, was largely consigned to the periphery of scientific thought. For decades, it remained a curious footnote in the grand story of the cosmos, an elegant but seemingly unnecessary piece of theoretical machinery. It was a solution in search of a problem. But while cosmologists built their beautiful, intricate models of the universe itself was quietly revealing that it was far stranger, far more perplexing than their equations had predicted. Two colossal cracks began to appear in the foundations of our understanding, deep fissures that threatened to bring the entire edifice tumbling down. It was from these deepening chasms of cosmic uncertainty that the primordial black hole would be resurrected, dragged from the dusty archives of theory to become a prime suspect in the two greatest unsolved mysteries of our time. The first mystery is one of profound and humbling ignorance. Look out at the universe, at the breathtaking tapestry of galaxies spiraling through the void, and you are seeing only the barest fraction of what is actually there. All the stars, the planets, the nebulae, the shimmering dust clouds, every single thing you could ever see or touch, all the atoms that make up you and me and the world around us, all of it amounts to a pathetic 5% of the cosmic inventory. The rest, a staggering 85% of the mass in the universe, is something else entirely. It is dark matter. It is the invisible scaffolding upon which galaxies are built, the unseen gravitational glue that keeps them from flying apart as they spin. We know it's there not because we see it, but because we see its commanding influence on everything we can see. We see its phantom grip in the dizzying speed of stars orbiting galactic centers, moving far too fast to be tethered by visible matter alone. It's like watching a child on a merry-go-round spinning at an impossible velocity held in place not by a visible metal bar, but by some immense unseen force. That force, that gravitational anchor, is dark matter. We see its presence in the way it bends the very fabric of space-time. When we look at distant clusters of galaxies, we witness a phenomenon called gravitational lensing, where the light from even more distant objects is warped and magnified as it passes through the cluster. The amount of distortion is titanic, far greater than all the visible stars and gas in the cluster could possibly produce. It reveals a colossal invisible reservoir of mass, a city of gravity, whose inhabitants are completely dark. This celestial ghost story is even etched into the oldest light in the universe, the cosmic microwave background. The subtle temperature variations in this afterglow of the Big Bang tell us precisely how matter was clumped together in the infant cosmos. The patterns we observe only make sense if there was a vast invisible component of matter that didn't interact with light, a substance that began to collapse under its own gravity long before normal matter could. This dark matter provided the gravitational wells, the cosmic potholes into which normal matter later fell to form the first stars and galaxies. Without it, we simply wouldn't be here. The universe as we know it would not exist. For decades, the search for this missing substance has been one of the most monumental undertakings in the history of science. The leading hypothesis was elegant and compelling. Physicists proposed the existence of a new type of subatomic particle, a creature from beyond our standard model of physics. They were given the name WIMPs, or weakly interacting massive particles. These theoretical particles would be heavy, they would be slow-moving, and crucially, they would interact with normal matter only through the weak nuclear force and gravity. They were the perfect suspect, invisible, abundant, and just interactive enough that we might, if we were very careful and very lucky, be able to detect one. And so we began to listen. We built extraordinary detectors, technological cathedrals buried deep underground to shield them from the constant rain of cosmic rays. We constructed vast vats of supercooled liquid xenon and germanium crystals waiting in absolute silence for the faintest whisper of a WIMP bumping into one of our atoms. Experiments like the Large Underground Xenon Detector and its successor Lux Zeppelin became our ears pressed against the wall of the dark universe. Years turned into decades. The sensitivity of our detectors increased by orders of magnitude. We built bigger, colder, quieter experiments pushing the very limits of technology, and the universe answered with a profound and deafening silence. The promised particle, the ghost that should have been flitting through the very room you are in right now, never showed up. It never knocked on the door. With each passing year of null results, the tension in the physics community has grown. The beautiful, simple picture of the WIMP is fading, its favoured hiding places all but eliminated. Other candidates like the wispy and ethereal Axion are still being pursued with incredible ingenuity. But the feeling is inescapable. We may have been looking for the wrong thing entirely. We've been searching for a new particle, a new force, a new chapter in the standard model. What if the answer isn't new physics at all? What if the solution has been hiding in the oldest physics we know, the physics of gravity itself taken to its most extreme conclusion? This is where the primordial black hole steps out from the shadows. Suddenly, it is no longer a mere curiosity. It is a radical, audacious, and deeply compelling candidate for the dark matter that has eluded us for so long. Consider its properties. A primordial black hole is by its very nature dark. It does not emit or reflect light. It is composed of the familiar stuff of the universe, matter and energy, but crushed into a form that makes it non-baryonic for all practical purposes, meaning it doesn't participate in the nuclear reactions that forge elements. It interacts with its surroundings almost exclusively through gravity. It is the ultimate stealth object. If the universe were filled with a diffuse swarm of these ancient relics, they would behave on a grand cosmic scale exactly like the dark matter we observe. They would provide the gravitational scaffolding for galaxies. They would bend the light of distant quasars. They would have clumped together in the early universe, creating the gravitational seeds for the structures we see today. They check every box. The idea is breathtaking in its simplicity. The universe's missing mass isn't some exotic, undiscovered particle. It is a population of invisible gravitational traps forged in the first moments of creation, scattered throughout the cosmos like a fine dark dust. This hypothesis opens up a vast landscape of possibilities, because unlike WIMPs, which were theorized to have a specific mass, primordial black holes could exist across an immense range of sizes. They could be as light as an asteroid drifting silently through interstellar space. They could be 100 times the mass of our sun wandering the dark voids between galaxies. They could even be thousands of times more massive, lurking in the hearts of the small, dense star clusters that orbit the Milky Way. Each mass range would produce different potentially observable effects, a set of fingerprints we might be able to find. The tantalizing possibility is that we haven't found dark matter because we've been using the wrong kind of detector. We've been listening for the whisper of a particle when we should have been looking for the shadow of a singularity. It reframes the entire search, transforming it from a particle physics problem into an astronomical hunt. The evidence we need may not be buried in a mile of rock, but hiding in plain sight in the terabytes of data streaming from our telescopes every single night. The ghost in the machine of cosmology was no longer a ghost. It had become a prime suspect, and it was about to be implicated in a second, equally profound cosmic crime. While particle physicists were grappling with their silent detectors, astronomers peering back to the dawn of time were confronting an entirely different kind of monster. Using instruments like the Hubble Space Telescope and the giant observatories of Earth, we have learned to look back in time to see the universe not as it is today, but as it was in its infancy. We expected to see a young, simple cosmos. We expected to see the first small tentative galaxies, clumsy collections of the first generation of stars slowly and patiently assembling themselves over billions of years. What we found instead, staring back at us from the edge of cosmic dawn, was shocking. We found titans. We found quasars, galactic cores ablaze with a ferocious light powered by supermassive black holes that are billions of times the mass of our own sun, and these were not mature objects in a mature universe. We found them when the cosmos was less than 1 billion years old, a mere fraction of its current age. It was like looking at a photograph from the year 1800 and seeing a fully built, fully populated Tokyo. It makes no sense. Take the quasar known as J313-1806. Its light has travelled for over 13 billion years to reach us. We are seeing it as it was when the universe was only 670 million years old. That is astonishingly early a time when the first galaxies were just beginning to switch on. Yet at the heart of this infant galaxy lurks a black hole that has already accumulated 1.6 billion solar masses. This object presents us with a terrifying paradox, a deep and fundamental crisis for astrophysics. How does something that big grow that fast? Our standard model for the formation of supermassive black holes is a story of patient, steady growth. It begins with the death of a single massive star, which collapses to form a stellar mass black hole perhaps 10 or 20 times the mass of the Sun. This seed black hole then begins to feed, slowly pulling in gas and dust from its surroundings. Occasionally it might merge with another stellar black hole, gaining a little more mass. Over eons, through a combination of steady accretion and occasional mergers, it can gradually build itself up into a monster. This model works perfectly well to explain the supermassive black hole in our own galaxy, Sagittarius A star, which has had 13.8 billion years to grow. But it utterly fails to explain J03131806 and others like it. There simply wasn't enough time. The universe was too young. Even if a seed black hole formed from the very first stars and began accreting matter as fast as physically possible, a theoretical limit known as the Eddington limit, where the outward pressure of the radiation from the feeding frenzy balances the inward pull of gravity, it still could not reach a billion solar masses in just a few 100 million years, is a mathematical impossibility. It's like trying to fill an entire reservoir with a drinking straw in under an hour. The timeline does not compute. The universe of our models is a universe of gradual construction. The universe we actually observe is a universe that contains skyscrapers on day one. Astrophysicists have tried desperately to solve this riddle. Perhaps the first stars were much more massive than we think, creating larger initial seeds of a few hundred solar masses. It helps, but it still isn't enough to bridge the gap. Perhaps dense star clusters could have undergone a runaway collapse, with stars merging together in a chaotic frenzy to directly form an intermediate mass black hole of 1,000 solar masses. This direct collapse model is a more promising avenue, but it requires a very specific and perhaps very rare set of pristine environmental conditions in the early universe conditions that might not have been common enough to explain the number of early quasars we're now discovering. Every conventional pathway we can imagine seems to be a desperate race against a clock that is impossibly fast. The growth curve is too steep. The problem isn't just a small discrepancy, it's a fundamental challenge to our understanding of cosmic evolution. And this is where our first mystery collides head-on with our second. This is where the dark matter suspect becomes the prime suspect in the case of the impossible giants. What if the first supermassive black holes didn't have to start from scratch? What if they didn't begin as a tiny stellar mass seed and desperately claw their way up to a billion solar masses against an unforgiving clock? What if instead they were born with a massive head start? What if the universe came pre-packaged with a population of ready-made, massive black hole seeds? Primordial black holes forged not from a star, but from the raw compressed energy of the Big Bang itself could have been those seeds. A primordial black hole with a mass of, say, 100,000 suns could easily have formed in the ultra-dense conditions of the first second of time. Such an object lurking in the heart of one of the first collapsing clouds of gas would act as a devastatingly effective gravitational seed crystal. It wouldn't need to be built. It was already there. It would immediately begin to pull in vast quantities of primordial hydrogen and helium growing at a ferocious rate. It completely short-circuits the growth problem. You're no longer trying to fill a reservoir with a straw. You're starting with a lake and turning it into an ocean. The existence of these massive primordial seeds would make the appearance of billion solar mass quasars in the early universe not just possible, but inevitable. They become the natural outcome of providing the infant cosmos with prefabricated foundations of immense gravity. Suddenly, the impossible giants seem less like a paradox and more like a clue, a blinking neon sign pointing back to the most violent and mysterious epoch in all of cosmic history. This single elegant hypothesis offers a potential solution to two of the most profound and disconnected problems in cosmology. On the one hand, a vast swarm of smaller asteroid-mass primordial black holes could be the invisible dark matter that holds our galaxies together. On the other, a rarer population of much larger city-mass primordial black holes could be the seeds that grew into the supermassive monsters we see at cosmic dawn. Could they be one and the same? Could the same physical process in the early universe have produced a wide spectrum of these objects from pebble-sized to star-sized, to sizes that dwarf entire star clusters? It is a staggering thought. The very fabric of our universe, the invisible architecture of galaxies and the monstrous engines at their hearts, could all be the direct inheritance of instabilities in the first fraction of a second of the Big Bang. It would mean that the answers to our biggest questions about the cosmos today are not to be found in the behaviour of exotic new particles, but in the echoes of that initial unimaginable explosion. The primordial black hole, once a theoretical ghost, now stands as a unified theory for our darkest cosmic puzzles. But a compelling story is not enough. Science demands evidence. A suspect, no matter how perfect the motive and opportunity, must eventually be found at the scene of the crime, and so the search is on. The hunt has begun to find a fingerprint, a shadow, a whisper of a gravitational echo from these ancient invisible wanderers. The great cosmic detective story has moved from theory to a direct, exhilarating and profoundly difficult search for the truth. And so we were left with a monolithic image, a single suspect in the grand cosmic mystery of dark matter. The primordial black hole born from a simple, brutal collapse in the universe's first second. A powerful idea, yet also a strangely confining one. It implied a universe that even in its most chaotic moment was somehow uniform in its creation of these strange objects. A single event, a single mechanism, a single type of ghost. But the early universe was anything but simple. It was a cauldron of forces and energies we can now only glimpse through the lens of mathematics and particle accelerators. And when we dare to look closer to truly immerse ourselves in the physics of that first impossible instant, the picture shatters. The single monolithic suspect fractures into 1,000 faces, a gallery of possibilities, a hidden family of cosmic phantoms, each born in a different crucible of creation. The stage for this diversification, the ultimate engine of potential, was inflation. That fleeting, ferocious epoch lasting less than a trillionth of a second, when the universe swelled from a point of unimaginable density to a vastness that would dwarf galaxies. We've understood it as the event that made our universe large, flat and uniform. But within that explosive expansion lies a secret, a mechanism not for smoothing things out, but for creating seeds of structure. Imagine the inflationary field, the very energy driving this expansion, not as a placid sea, but as a roiling ocean of quantum potential. Everywhere, at every moment, tiny fluctuations, ripples of energy, were constantly popping into and out of existence, ghostly particles appearing and annihilating in the quantum foam. In our universe today, these fluctuations are fleeting and insignificant. But during inflation, the universe was expanding so violently, so mind-bendingly fast, that it would catch some of these ripples before they could disappear. It grabbed them, locked them in and stretched them. It stretched them from subatomic scales to astronomical ones. A tiny momentary quantum jitter, an ephemeral flicker of energy, could be inflated into a wave of density the size of a solar system. This is the heart of the matter. Inflation didn't just smooth the universe, it simultaneously sowed the seeds of its own imperfection. And within these vast, stretched out waves of energy, some regions would by pure chance be monumentally dense, peaks in the cosmic ocean, mountains of matter and energy so massive, so gravitationally potent, that the outward pressure of the Big Bang's explosion was no match for them. They had no stars to hold them up with nuclear fusion, no complex physics to resist their own overwhelming mass. There was only gravity raw and absolute, and so they collapsed, instantly. Without fanfare, without a supernova's dying cry, they simply winked out of existence, punching a hole in the fabric of space-time itself. They became primordial black holes. What makes this inflationary genesis so profound is its inherent randomness, its beautiful chaotic nature. The size of the quantum fluctuation determined the mass of the resulting black hole. A small flicker could create a black hole with the mass of a mountain, a slightly larger one the mass of an asteroid. A truly colossal yet still microscopic ripple could collapse into a PBH, with the mass of a moon or even a planet. There was no single preferred mass. Instead, inflation would have likely forged a vast continuous spectrum of them, a sliding scale of cosmic ghosts. Furthermore, the precise moment during that inflationary epoch when a fluctuation was frozen in would determine its characteristics. Different energy scales were at play from one instant to the next. This means you could have different populations of PBHs, entire generations, born fractions of a nanosecond apart each, with its own typical mass range, its own unique fingerprint imprinted upon the cosmos. The simple suspect had become a dynasty, a lineage of darkness stretching across the first moments of time each member, a direct physical relic of a specific quantum event at the dawn of existence. When you think of a primordial black hole born this way, you're imagining a fossilized quantum wave, a ghost of the universe's most violent expansion, still haunting the cosmos 14 billion years later. But this cosmic forge, as powerful as it was, may not have been the only one. The universe as it cooled from the inferno of the Big Bang was not a placid, gradually changing environment. It went through a series of violent transformative convulsions known as phase transitions. You have witnessed phase transitions your entire life. It's what happens when steam condenses into water or when water freezes into ice. The substance is the same, but its fundamental state, its physical properties change abruptly and dramatically. The early universe underwent phase transitions far more profound than the freezing of water. These were moments when the very laws of physics changed. Imagine a time a bare microsecond after the Big Bang, when the electromagnetic force and the weak nuclear force which governs radioactive decay were not separate. They were unified, a single symmetric electro-weak force. The universe was too hot, too energetic for them to have separate identities. But as the cosmos expanded and cooled, it reached a critical temperature. The symmetry broke. The electro-weak force froze, crystallizing into the two distinct forces we know today. This was not a gentle process. Like supercooled water suddenly flashing into ice, it would have been violent. Across the universe, bubbles of the new physics, our physics, would have spontaneously appeared and expanded at nearly the speed of light. This was the universe we recognize being born, but it was being born in a cataclysm. As these bubbles of true vacuum grew and collided, they would have created unimaginable shockwaves in the primordial plasma. At the intersection of these cosmic collisions, vast amounts of energy could be trapped and concentrated into infinitesimally small points. Energy densities so high they would momentarily recreate the conditions of the Big Bang itself. And what happens when you concentrate an immense amount of energy into a vanishingly small space? You create a black hole. Unlike the broad spectrum of masses from inflation phase, transitions would create PBHs with a very specific characteristic mass, a mass directly tied to the energy scale of the transition itself. The electroweak phase transition, for example, would theoretically produce a population of primordial black holes, all weighing about the mass of a planet like Earth. Not a range, but a specific signature. A monochromatic signal. Think of it scattered across the universe, a population of black holes, each weighing 3 million billion tons each, a tombstone marking the exact moment the forces of nature split apart. And this was just one transition. Physicists theorize another even earlier one called the QCD transition, when quarks and gluons, once free in a quark-gluon plasma, became confined inside the protons and neutrons that make up you and me. This transition too could have been violent enough to forge its own distinct population of PBHs, this time with a mass closer to that of our Sun. Suddenly the picture becomes richer, more complex, more elegant. We now have multiple mechanisms operating at different times at different energy scales, each creating its own unique family of objects. Inflation provides the broad foundational noise, a chorus of masses across the board. Phase transitions provide the sharp, resonant notes, specific frequencies of black holes singing a song of cosmic change. The search for primordial black holes was no longer a hunt for a single footprint, but for an entire ecosystem of predators, each adapted to the unique environment of its birth. And the universe, in its boundless imagination, may have had even more exotic methods for crafting these objects of ultimate density. As the fabric of space-time itself cooled and settled into its final form, it may have developed defects, imperfections, not unlike the cracks that form in ice as it freezes. These are not cracks in a material, but topological defects in the geometry of space-time itself. One of the most tantalizing possibilities is the cosmic string. Not the strings of string theory, but vast one-dimensional filaments of pure energy, thinner than a proton, but stretching across unimaginable cosmic distances, possessing a tensile strength that would make steel seem like vapor. These strings, remnants of a high-energy phase of the early universe, would whip through space at nearly the speed of light, carrying the mass of entire galaxies in their tiny energetic cross-section. When two such strings crossed, or when a single string looped back on itself, they could form oscillating, self-gravitating loops. These loops would radiate their energy away as gravitational waves, shrinking and becoming denser until they reached a point of no return. They would collapse under their own impossible tension into a black hole. A PBH born from a cosmic string would be another species entirely a child of space-time's own structural flaws. And there could be other even stranger defects. Two-dimensional domain walls, vast membranes separating regions of the universe, with different physical laws whose collapse would be a truly universe-altering event, leaving behind clutches of gargantuan black holes. Or magnetic monopoles, isolated north or south magnetic poles, whose gravitational attraction could have pulled them together to form yet another class of primordial singularity. These ideas are at the very edge of theoretical physics, and they paint a portrait of the dawn of time as a place of terrifying, beautiful and creative violence. A place where the universe was not just expanding, but actively experimenting with the laws of nature, and where every experiment, every transition, every flaw had the potential to leave behind an eternal remnant, a black hole forged not from a star but from the very physics of creation. The singular idea of a PBH has been shattered. In its place, we find a rich and vibrant tapestry of possibilities. This revolution in thinking forces us to completely reevaluate what we're even looking for. We're no longer scanning the skies for one thing, we're scanning for everything. At the lowest end of the mass scale, we have the true phantoms, primordial black holes with the mass of a large building or even a human being. Born in the most energetic moments of inflation, these tiny singularities would be subject to the strange laws of quantum physics. They would leak. Through the process of Hawking radiation, they would slowly, inexorably evaporate their mass back into the universe as a faint fizz of particles and radiation. Those with masses less than a large asteroid would have already evaporated completely by the present day, disappearing in a final brilliant flash of gamma rays. Are these flashes the unidentified gamma ray bursts we sometimes see from the depths of space? Are we witnessing the death rattles of the universe's first objects, slightly more massive, and we enter the realm of the ultimate dark matter candidate? PBHs with the mass of asteroids, mountains or moons, these are the perfect lurkers. They are too small to emit any detectable Hawking radiation over the age of the universe. They are too tiny to easily spot through gravitational lensing. They don't burn, they don't shine, they don't interact. They just are. They would drift silently through the halos of galaxies, a cold, dark swarm of gravitational points, their collective gravity holding the cosmos together, while they themselves remain utterly infuriatingly invisible. Millions of them could be passing through our own solar system right now, and we would be completely unaware. This is the population that could solve the dark matter problem in its entirety, a perfect suspect that leaves no evidence save for the weight of its own existence. But the family tree extends to far greater sizes. Consider the planetary mass primordial black holes, the potential children of the electroweak phase transition. An object with the mass of Jupiter but compressed into the size of a marble. Such an object, if it passed through our solar system, would be undetectable by telescope. Yet its gravity would be immense. It could subtly perturb the orbits of the outer planets, tugging on comets in the Oort cloud, creating anomalies in the cosmic architecture that we are only now beginning to notice. Could the mysterious hypothetical Planet 9, the unseen gravitational influence at the edge of our solar system, not be a planet at all? Could it be one of these ancient relics, a dark wanderer from the first microsecond of time, now silently sharing our celestial home the mathematics permit it? The possibility is astonishing. We have been searching for a world when we should perhaps have been searching for a hole in the world. And the scale continues to grow. Stellar mass PBHs forged by the QCD transition, or by colossal inflationary fluctuations, could be masquerading as normal astrophysical black holes today. When our gravitational wave detectors register the merger of two black holes, we assume they are the corpses of dead giant stars. But how can we be sure? Could some of them be pristine artifacts from the Big Bang objects with no stellar parents, no history of fusion and fire that have finally found each other after a 14 billion year dance in the dark? Their spin, their mass distribution might hold the clues. They might be too heavy or too light to have formed from a star, a subtle tell that their origin lies not in a supernova, but in the primordial furnace. And finally we arrive at the Titans, the seeds of monsters. One of the great puzzles in modern cosmology is the existence of supermassive black holes at the centres of galaxies' behemoths, weighing millions or even billions of times the mass of our Sun. We see them in the very early universe, already fully formed at a time when there simply hasn't been enough time for a normal stellar mass black hole to grow that large by eating gas and stars. It's a paradox, a timeline that doesn't add up. Primordial black holes offer a breathtaking solution. What if the universe didn't have to build these monsters from scratch? What if the most extreme density fluctuations during inflation created seed, black holes already thousands of times the mass of the Sun in the first second of existence? These seeds would then simply wait. They would act as gravitational anchors, cosmic anchors in the primordial soup, around which the first gas would cool, the first stars would ignite, and the first galaxies would form. Our entire galactic history, the story of the Milky Way itself, might not be one of building a central black hole, but of growing around a pre-existing primordial progenitor. We may not just live in a galaxy with a black hole at its centre. We may live in a galaxy that owes its very existence to a leftover from the dawn of time. From evaporating quantum ghosts to the seeds of galactic empires, the scope of what a primordial black hole could be has exploded into a menagerie of cosmic possibilities. This is the pivotal turn in our investigation. We are no longer chasing a single shadow. We are now faced with the staggering realization that there could be an entire dark ecosystem, a complex web of objects of different sizes, origins and influences woven into the very fabric of the cosmos. A population of asteroid mass objects making up the dark matter halo, a separate population of planetary mass objects wandering interstellar space, another population of stellar mass objects mimicking their stellar cousins, and a sparse population of giants sitting enthroned in galactic cores. This is no longer a simple theory. It is a framework for a second unseen universe, a shadow biosphere of gravity. The question, now more urgent and more complex than ever, becomes our new guide. If this vast diverse family of cosmic remnants truly exists born from the cacophony of the Big Bang, then where are they? How in this silent darkness across this vast spectrum of possibility do we finally design an experiment, a search, an observation that will allow one of these ghosts to give itself away? The hunt is about to begin, and so the gauntlet was thrown. With theory revitalized, the abstract elegance of primordial black holes demanded a confrontation with reality. It was no longer enough to imagine these cosmic relics. We had to find them. The hunt was on a search that would push human ingenuity to its absolute limits, transforming the entire cosmos into a laboratory and every telescope into a potential witness. This was not a search for a single object in a single patch of sky, but a sprawling multi-pronged investigation across all of space-time, from our galactic backyard to the faint echo of the Big Bang itself. It would become one of the most challenging and at times profoundly frustrating quests in modern astrophysics. The universe, it seemed, was exceptionally good at keeping its oldest secrets. We would have to be exceptionally clever to trick it into telling. One of the first traps laid for these gravitational ghosts relies not on seeing them, but on feeling their immense weight as they drift unseen through the galactic wilderness. This ingenious method is called gravitational microlensing. Imagine you are staring at a distant steady star, a single point of light in the celestial tapestry. Now imagine a massive unseen object, a primordial black hole perhaps drifting silently across your line of sight. According to Einstein's general relativity, its gravity doesn't just pull on things, it fundamentally warps the fabric of space-time around it. As the PBH passes in front of the distant star, this warped space-time acts like a lens, a celestial magnifying glass forged from pure gravity. For a brief precious moment, the light from the background star is bent and focused, causing the star to appear to brighten dramatically, then fade back to normal as the invisible object continues its journey. This transient symmetrical brightening is the telltale signature, the fingerprint of a massive compact object passing by. It's a way to see the invisible, to detect a presence through its gravitational shadow alone. In the 1990s, ambitious projects like the MACO Massive Astrophysical Compact Halo Object Survey and OGLE, the Optical Gravitational Lensing Experiment, began to systematically monitor hundreds of millions of stars night after night. They were hunting for these very flickers in the dark, hoping to catch a PBH in the act. The sheer scale of the undertaking was monumental. It was like watching an entire city of light bulbs, hoping to see one momentarily flare up because a tiny invisible marble had passed in front of it. And they did find events. They saw stars brighten and dim exactly as predicted. But here the universe threw a wrench into the works. The problem is that a primordial black hole isn't the only thing that can create a microlensing event. Any compact dim object will do. A faint brown dwarf, a wandering neutron star, or even a rogue planet ejected from its home system could all produce an identical light curve. The duration of the brightening gives you a clue about the mass of the lensing object. A shorter event implies a smaller mass. The surveys were looking for events corresponding to a wide range of masses from planet-sized PBHs to those many times the mass of our Sun. The results that trickled in were a complex mix of triumph and ambiguity. The experiment successfully demonstrated that our galaxy's halo was not in fact filled with vast numbers of stellar mass compact objects. This placed the first powerful constraints on certain theories, effectively ruling out the idea that all of dark matter could be composed of primordial black holes with masses similar to our Sun. The window of possibility began to narrow, yet for smaller masses the picture remained stubbornly murky. Shorter duration events which could correspond to asteroid mass or planet mass PBHs were exceptionally difficult to detect with the technology of the time. The Earth's own atmosphere blurs our view, and the cadence of observations, how frequently you can photograph the same patch of sky, meant that these fleeting flickers could easily be missed entirely. You're searching for a needle in a cosmic haystack, and the needle itself is only visible for a few hours or even minutes. It's a beautiful, elegant technique, a testament to our ability to use the laws of physics to our advantage, but it left us with a frustrating verdict, a lack of overwhelming evidence, but not definitive proof of absence. The phantoms remained at large, their existence neither confirmed nor denied, simply confined to a smaller, darker corner of the possibilities. But as the door on microlensing seemed to be closing, a revolutionary new window onto the cosmos was being forced open. For decades we had been deaf to the most violent symphonies of the universe. We could see their light, their afterglows, their wreckage, but we couldn't hear the fundamental sound of their collisions. That all changed on September 14th, 2015. On that day, 2 detectors, one in Louisiana and one in Washington state, felt a tremor. It was not a tremor of the Earth, but a tremor in the very structure of reality. For the first time, the Laser Interferometer Gravitational Wave Observatory, or LIGO, had detected gravitational waves, ripples in space-time itself, unleashed by the cataclysmic merger of 2 stellar mass black holes over 1 billion light-years away. It was a discovery that would win the Nobel Prize and give humanity a completely new sense with which to perceive the universe. And for those hunting the relics of the Big Bang, it was a game-changer. Suddenly, we had a way to listen for the whispers of primordial black holes colliding in the dark. A gravitational wave signal from 2 merging black holes is an astonishingly precise thing. It's a chirp, a sound wave that sweeps upwards in frequency and amplitude as the 2 behemoths spiral closer and closer, faster and faster, until they finally fuse into one ringing space-time like a cosmic bell. The exact shape of that chirp tells you everything: the masses of the 2 black holes, how fast they were spinning, even their orientation in space. This is where the hunt for PBHs gets incredibly interesting. If 2 black holes born from the collapse of giant stars merge, their spins are likely to be chaotic, misaligned from their orbit, a messy remnant of their violent birth. But if 2 primordial black holes born from the dense soup of the early universe were to find each other billions of years later, they would likely have very low or even zero spin. Their merger would produce a cleaner, simpler chirp. Furthermore, stellar black holes have a lower mass limit. You simply can't form one from a star that is less than a few times the mass of our Sun. Primordial black holes, however, have no such restriction. They could be lighter than our Sun, if LIGO were to detect a merger of two black holes each less than 1. For solar masses, the so-called Chandrasekhar limit, it would be almost impossible to explain through standard stellar evolution. It would be a smoking gun for a primordial origin. With every new detection, run LIGO and its European partner Virgo have been building a census of black hole mergers. They have found dozens a population of cosmic leviathans we never knew existed in such numbers. And within that growing catalogue there are tantalising hints. Some mergers involve black holes with unusually low spins. Others fall into a mass gap where stellar-born black holes are not expected to exist. And then there was the event GW19 Fatudu-1, a merger that produced a final black hole of about 142 solar masses, placing it firmly in a forbidden range for stellar evolution, a class known as intermediate mass black holes. Could this be the result of a hierarchical merger, where smaller PBHs merged over cosmic time to build up to this size? The data is provocative, suggestive. But it is not yet conclusive. A merger of two primordial black holes would also lack a key feature present in other cosmic collisions. If a neutron star merges with a black hole, the star is torn apart before being swallowed, a process called tidal disruption that can unleash a brilliant flash of light across the electromagnetic spectrum. But a primordial black hole merger, two pure featureless points of gravity, would be utterly dark. No light, no gas, no fireworks. Just a pure, unadulterated tremor in space-time. The challenge then is to accumulate enough of these gravitational wave events to build up a statistical case to separate the truly strange signals from the already bizarre behaviour of stellar-born black holes. We are listening intently to the gravitational symphony, hoping to discern a new instrument playing a tune composed at the dawn of time. While microlensing and gravitational waves probe our local universe, other methods allow us to cast our gaze back much, much further to the very edge of cosmic history. We can scrutinise the universe's baby picture, the cosmic microwave background, or CMB. This is the faint residual glow of the Big Bang, an almost perfectly uniform sea of radiation that fills all of space. It's a snapshot of the universe when it was just 380,000 years old, a pristine photograph of the cosmos in its infancy. Almost perfect, but not quite. The tiny temperature fluctuations in the CMB are the seeds from which all galaxies, stars and planets would eventually grow. Its near perfection is one of the strongest pillars of modern cosmology, and that very perfection allows us to use it as a sensitive tool to hunt for primordial black holes. If a significant population of PBHs existed in that fiery early epoch, they would not have been entirely passive. Their immense gravity would draw in the surrounding hot gas and radiation. This process of accretion would have released enormous amounts of energy, injecting heat and light back into the primordial plasma. Think of it like dropping hot stones into a perfectly still, cool pond. The heat from the stones would disturb the water's uniform temperature, creating ripples and warm spots. In the same way, energy injected by accreting primordial black holes would have distorted the perfect blackbody spectrum of the CMB. It would have subtly altered the delicate pattern of its temperature fluctuations. In the 1990s, the COBE satellite gave us our first coarse map of this background radiation, followed by the much sharper views from WMAP and ultimately the breathtaking precision of the European Space Agency's Planck satellite. Planck mapped the CMB with such exquisite sensitivity that it could detect temperature variations of just a few millionths of a degree. Scientists could then take these incredibly precise maps and ask, is there any evidence of this extra energy injection? Are there any distortions that cannot be explained by standard cosmic evolution? They could run models of the early universe, seed them with different populations of PBHs of varying masses and abundances, and see what effect they would have on the final CMB we observe today. The results from Planck delivered a powerful blow to many primordial black hole theories. The CMB was to an astonishing degree perfect. Its spectrum and temperature anisotropies matched the predictions of the standard cosmological model with almost unnerving accuracy. There was simply no room for any significant energy injection from a large population of accreting PBHs. These measurements place some of the most stringent constraints yet on their abundance, especially for those in a wide mass range from about the mass of the Earth up to thousands of solar masses. It essentially drew a line in the sand. Primordial black holes in this range could not by themselves constitute the entirety of dark matter. The window of possibility once again shrank dramatically. It didn't rule them out entirely, of course. Perhaps they existed in numbers too small to leave a discernible trace. Or maybe they existed at masses outside the range to which the CMB is most sensitive, either very small or stupendously large. The pristine nature of the universe's first light had become a formidable barrier, a silent testament against the existence of a vast hidden population of cosmic fossils. The search was forced to move to even more extreme arenas. For the very smallest primordial black holes, those with the mass of a mountain or an asteroid, we hunt not for their gravity, but for their death. This brings us to one of the most exotic and mind-bending ideas in all of physics, Hawking radiation. In the 1970s, Stephen Hawking stunned the world by showing that black holes are not truly black. Due to bizarre quantum effects near the event horizon, they should leak a faint trickle of particles and radiation into space, causing them to slowly inexorably evaporate over immense timescales. This process is fantastically slow for a stellar mass black hole. One would take trillions upon trillions of times the current age of the universe to disappear. But the rate of evaporation is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it is and the faster it evaporates. A primordial black hole with the mass of a large mountain, about 1 billion tons, would have a lifetime roughly equal to the age of the universe. This means that any PBHs of this mass forged in the first second of the Big Bang would be reaching the final explosive moments of their lives right now. As such, a black hole evaporates, it shrinks, getting hotter, and radiating away energy more and more furiously. In its very last second of existence, it would unleash a tremendous burst of high-energy particles and gamma rays, a final desperate flash of energy, equivalent to millions of hydrogen bombs detonating in a microscopic point of space. This is the signature we can hunt for. We can use gamma-ray telescopes like the Fermi Gamma-Ray Space Telescope to scan the skies for these isolated, unexplained bursts of high-energy photons coming from a point in space with no obvious source like a supernova or a colliding neutron star. A detection would be unambiguous proof of both Hawking radiation and the existence of primordial black holes. It would be one of the greatest discoveries in the history of science. For decades we have been searching for these death cries, and for decades we have been met with silence. The Fermi telescope and other experiments have placed incredibly tight limits on the number of these evaporating black holes. The extragalactic gamma-ray background, a faint glow of high-energy light coming from all directions, also serves as a powerful constraint. If too many PBHs were evaporating throughout cosmic history, their combined death screams would make this background glow far brighter than what we observe. This consistent lack of detection has all but ruled out primordial black holes in this very low mass range as a major component of the universe. The web of constraints tightens ever further. We've looked for their gravitational influence on starlight and found little. We've listened for the sound of their collisions and heard only tantalizing but inconclusive whispers. We've searched for their energetic fingerprints on the baby picture of the universe and found the picture to be pristine. We've listened for their dying screams and have been answered only by the vast, quiet darkness. Each new experiment, each null result has chiseled away at the realm of possibility, corralling these elusive phantoms into ever narrower corridors of mass and abundance. It paints a picture not of failure, but of science working at its best, the relentless systematic interrogation of nature. The hunt has become a process of elimination, a grand cosmic Sudoku, where every constraint filled in gets us closer to the final solution. The question is no longer just, where are they, but where can they be? And as the observational walls close in, theorists are being forced into stranger, more creative territory, proposing new formation mechanisms and new signatures that might just have slipped through our formidable net. For what if the most profound clues were not to be found by looking out, but by looking within? What if these relics of creation were not just passing through our world, but were on the rare occasion captured by it? And so, the great cosmic dragnet woven from the light of distant stars, the faint heat of the universe's afterglow, and the complex dance of galaxies has been pulled through the vast ocean of possibility. For decades we have searched for these ghosts from the dawn of time, and in one mass range after another the net has come up empty. The constraints have tightened, squeezing the primordial black hole hypothesis from a broad sweeping speculation into a fugitive cornered theory. The walls, it seems, are closing in, but this is not a story of failure. It is a story of refinement. The hunt has become more precise, more focused, more thrilling. Because in the shrinking territory left for these ancient relics, we find not just lingering possibilities, but profound solutions to some of the most stubborn paradoxes in cosmology. The very act of eliminating where they are not has illuminated with stunning clarity where they must be if they exist at all. We're no longer looking for a needle in a haystack. We're now examining a few specific strands of hay that glow with a strange, unaccountable light. These are the windows of survival. The first and perhaps most tantalizing of these windows opens onto a population of objects so humble in scale yet so vast in number that they could form the very bedrock of the cosmos. Imagine a black hole no larger than a mountain, or even a city block with the mass of a large asteroid. Objects in this range, from about 100 trillion tons up to the mass of our own moon, have masterfully evaded our gaze. They are too small to trigger the powerful gravitational lensing events that our surveys are tuned to detect from star-sized objects. A brief flicker from a background star as one passes by would be too faint, too ephemeral for our current telescopes to reliably capture. They are in essence gravitationally invisible at vast distances. Simultaneously, they are just massive enough to have resisted the ultimate fate of their even smaller brethren, complete evaporation. Hawking radiation, that slow quantum sizzle that bleeds a black hole's energy away, would take quadrillions of years to dissolve an object of this scale. They are for all practical purposes permanent fixtures of the universe, as stable as the protons in your own body. So here we have a perfect cosmic culprit, a population of primordial wanderers born in the first second of time, too small to be seen yet too large to have faded away. They would not emit light nor absorb it nor interact with our world in any way except for their collective overwhelming gravity. Could this be it? Could the dark matter we've sought for nearly a century be nothing more than a silent, unseen blizzard of mountain-sized black holes drifting through the void between the stars, outnumbering all the atoms in all the galaxies combined? It's an idea of staggering elegance. It requires no new particles, no new forces, no exotic physics beyond what we already know and understand. It simply requires that the infant universe was a far more violent, chaotic place than we have previously dared to imagine, a crucible that forged not only the seeds of light, but a parallel unseen creation of pure gravity. These asteroid mass relics would form the immense invisible halos we observe around galaxies, their gravitational grip the silent architect of the cosmic web. They are the perfect cosmic ghosts, their presence felt everywhere, their forms seen nowhere. But another window remains open in a completely different part of the mass spectrum, and peering through it reveals a suspect that would be, if found, even more definitive. This is the sub-solar window, black holes with masses less than our own sun but significantly larger than an asteroid, say the mass of Jupiter, or even 20 Jupiters. Here the argument for their primordial origin becomes ironclad. Astrophysics as we understand it simply cannot make black holes this small. The modern universe manufactures its black holes from the death of giants. A star must be immense, at least 20 or 30 times the mass of our sun, for its core to collapse under its own weight, with such force that it punches through the fabric of space-time itself. The process has a minimum threshold. A star the size of our sun or smaller will never become a black hole. It will live out its life and fade into a gentle cooling ember, a white dwarf. Nature today has no mechanism for creating a black hole with the mass of a planet. Therefore, if we were ever to detect such an object, its origin would be unmistakable. It could not be the child of a dead star. It would have to be something else, something ancient, a true relic. And unlike the asteroid mass phantoms, these subsolar black holes are not entirely beyond our reach. They are massive enough that when two of them spiral together in a final catastrophic embrace, They would send a shockwave through the cosmos, a pulse of gravitational waves. Our existing detectors, LIGO, Virgo and Kagra, are gravitational observatories tuned to precisely this kind of event. Every chirp they detect is the sound of a cosmic collision, a sound that tells us the masses of the objects that merged. To date, they have heard the songs of merging stellar mass black holes, each one dozens of times the mass of our Sun, consistent with stellar death. But they are listening, and if one day they hear a different song, a higher-pitched chirp from the merger of two objects far lighter than any known star could produce, the debate would be over. It would be the first direct incontrovertible evidence of a creature from the Big Bang, a primordial fossil, speaking to us across 13.8 billion years. These windows offer a breathtaking solution to the puzzle of dark matter. But the evidence for primordial black holes doesn't stop there. It extends to a completely different cosmic enigma, one that concerns not the unseen scaffolding of the universe, but the brilliant monstrous hearts of the galaxies themselves. We now know that at the centre of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational singularity millions or even billions of times the mass of our Sun. These are the engines of cosmic evolution, the gravitational anchors around which entire galactic systems pivot, and their existence presents us with a profound paradox of time. When we use our most powerful telescopes to look deep into space, we're also looking back into the past. And in the faint light from the universe's infancy, we see things that should not exist. We see quasars, galactic cores blazing with the light of 1 trillion stars, powered by black holes already 1 billion times the mass of our Sun. And we see them when the universe was less than 1 billion years old. This is an impossible timeline. How do you grow a monster that big, that fast? The standard model tells us that black holes grow by feeding on gas dust and stars, and by merging with other black holes. But there is a physical limit to how fast a black hole can eat. It's a process that takes time, immense spans of cosmic time. Starting from a single star-sized black hole, even if you provide it with an endless buffet of material, it simply is not possible to grow it to 1 billion solar masses in the short time available in the early universe. It's like trying to build a skyscraper in a single afternoon using only one worker. The math just doesn't add up. For decades, this has been one of astrophysics' most urgent problems. The universe we observe does not match the universe our models can create. There is a missing ingredient, a cheat code, a head start. This is where primordial black holes re-enter the story not as passive dark matter, but as active cosmic architects. What if the universe didn't have to build its giants from scratch? What if the seeds of these monsters were forged directly in the Big Bang itself? Imagine primordial black holes, not with the mass of asteroids, but with the mass of 1,000 suns or 10,000. These intermediate mass black holes, born from the same cosmic violence that might have created their smaller cousins, would be gravitational anomalies. They would have formed in an era before the first stars had even ignited. Scattered throughout the primordial gas clouds of the infant cosmos, they would have acted as irresistible gravitational magnets. They would be the anchors, the dense cores around which the first galaxies could coalesce. Instead of gas slowly clumping together over hundreds of millions of years to form a star which then dies, to form a small black hole, these ancient seeds would have skipped the entire process. They were the ready-made foundations. The first galaxies didn't have to build a central black hole, they were born around one. This single, elegant idea solves the timeline problem instantly. Our supermassive black holes didn't grow impossibly fast. They just had a tremendous head start. They were not just remnants of the Big Bang, they were its heirs, the gravitational royalty around which the lesser matter of the universe would bend the knee, organising themselves into the first great cosmic empires. The very structure of the universe as we know it today, the grand spiral of the Milky Way, the existence of our solar system, our planet, our lives may be a direct consequence of these primordial giants. So we stand at a precipice, a moment of profound tension. On one side, we have an accumulation of circumstantial evidence that is almost too compelling to ignore. A theory that potentially solves not one but two of the greatest mysteries in all of science, the nature of dark matter and the origin of supermassive black holes. On the other side, we have silence. a complete frustrating lack of definitive direct detection. It is the ultimate cosmic cliffhanger. The suspects have been identified, their motives are clear, and their hiding places have been narrowed to a few distinct possibilities. All that is missing is the smoking gun. But that is about to change. We're on the eve of a revolution, a time when our ability to perceive the universe is about to undergo a fundamental transformation. For most of human history, we have studied the cosmos with our eyes gathering its ancient light. But we've been deaf to its deepest sounds. Gravitational wave astronomy has given us a new sense. We're no longer just watching the universe. We're beginning to listen to it. We are listening to the rhythm of space-time itself, to the vibrations left by the most violent and powerful events since creation. And with this new sense, we are building an instrument so ambitious, so audacious in its scale, it will allow us to hear the whispers from the dawn of time. It is called LISA, the Laser Interferometer Space Antenna. It is not a telescope on Earth, but a celestial instrument of cosmic proportions. 3 separate spacecraft flying in a perfect triangular formation trailing the Earth in its orbit around the Sun. Each spacecraft is separated from the others by 2.5 million kilometers. They will be linked by laser beams measuring their separation with a precision so exquisite it can detect a change smaller than the width of a single atom. This immense triangle is not just a machine, it is a web. A gravitational antenna designed to feel the most subtle tremors in the fabric of reality. LISA is tuned to a different cosmic frequency than its ground-based cousins. While LIGO hears the high-pitched chirps of colliding stellar mass black holes, LISA will listen for the deep low-frequency rumble of merging giants. If intermediate mass primordial black holes, the seeds of galaxies, truly exist, LISA will hear them. When 2 of these 1,000 solar mass relics spiral into one another, their gravitational siren song will be precisely in the frequency band LISA is designed to detect. It will not be a fleeting chirp, but a powerful, unmistakable signal, one we could track for weeks, months, or even years as the 2 objects draw closer to their final cataclysmic union. The detection of even one such event would be transformative, providing the first direct proof that these ancient seeds are real. But LISA's quest goes even deeper. It will listen for something even more profound, the stochastic background. A persistent quiet hum of gravitational waves coming from all directions at once. This would be the echo of the universe's most chaotic moment. If the Big Bang produced a truly vast number of primordial black holes, the sheer violence of their formation, a process of cosmic boiling and collapsing, would have churned space-time on a massive scale. The result would be a residual background of gravitational waves, a faint static that has been travelling across the cosmos ever since. It would be the sound of creation itself. To detect this hum would be to hear the birth cries of the universe, and within that sound we could find the definitive signature of a primordial black hole population. And while LISA prepares to listen for the giants here on Earth, a new generation of gravitational observatories is being designed. The Einstein telescope in Europe, a vast triangular instrument buried deep underground. Cosmic Explorer in the United States with arms 40 kilometers long. These machines will be so sensitive they will register nearly every single stellar mass black hole merger in the entire observable universe. Their reach will be absolute. If a population of sub-solar mass primordial black holes exists and is merging, these new observatories will find them. Their silence, on the other hand, would be just as telling, allowing us to finally close that window for good. The era of ambiguity is ending. We have arrived at the moment of reckoning. The theory, once a fringe idea, has been honed and sharpened by decades of inquiry. The circumstantial evidence points compellingly towards a universe seeded with the gravitational remnants of its own birth. The technology to provide the final, incontrovertible proof is no longer the stuff of science fiction. It is being forged, tested, and prepared for launch. We are moving from an age of inference to an age of direct interrogation. The question is no longer solely in the hands of the theorists. It is now in the hands of the engineers, the experimentalists, the explorers. The verdict on one of the deepest and oldest secrets of the cosmos is about to be read. And when it is our entire understanding of the universe's architecture, from the invisible matter that holds it together to the brilliant galaxies that light it up, may be fundamentally and forever transformed, the silence is about to be broken. And so with these extraordinary blueprints for our future eyes and ears, our cosmic detective story approaches its climax. We stand on the precipice of a new era of perception, preparing to listen for the faintest whispers from the dawn of time itself. Our journey together has taken us from the chalkboards of Cambridge, where the audacious ideas of Hawking and Carr first took flight, to the sterile cleanrooms, where the world's most sensitive instruments are born. We have sifted through the afterglow of creation, the cosmic microwave background for the subtlest of shadows. We have listened to the symphony of space-time played by colliding stellar giants, hoping to catch an unexpected note, a primordial accent in that gravitational chorus. We have stared into the darkness between the stars, searching for the flicker of a microlensing event, a fleeting distortion caused by an invisible wanderer passing silently in the night. The quest for primordial black holes has been a magnificent and at times profoundly frustrating exercise in chasing ghosts. For decades, they were little more than a beautiful theoretical construct, an elegant but unproven footnote in the grand saga of the Big Bang. They existed in the tangled equations of general relativity and the speculative daydreams of cosmologists, but nowhere, it seemed, in the tangible universe we could observe. The evidence remained stubbornly elusive, a series of tantalizing hints and frustrating dead ends. The search was a process of elimination, a slow carving away of possibilities, defining these ancient objects more by where they were, not than by where they were. They could not be too small, or their explosive deaths would have scarred the cosmos with gamma rays. They could not be too large or too numerous, or their gravitational influence would have warped the paths of stars in ways we simply do not see. Yet with every constraint we placed upon them, with every observational window we closed, the mystery only deepened. The ghost became more defined. We were no longer hunting for a vague notion, but for a very specific kind of quarry, lurking within specific mass ranges, their potential signatures calculated with increasing precision. What began as a whisper in the lecture halls has now become a thunderous unifying question at the forefront of astrophysics. The search has evolved from a fringe speculation into one of the most compelling and critical investigations in all of science, because the stakes are nothing less than the very foundations of our cosmic understanding. Finding them would not just add a new object to the celestial zoo, it would force us to rewrite the opening chapters of cosmic history. This is because the discovery of a primordial black hole would be the ultimate validation of a universe born in unimaginable violence and chaos. Our current models of cosmic inflation depict the newborn universe as a nearly perfect, smooth, and featureless expanse, expanding at a hyper-accelerated rate. But to create a primordial black hole, you need the opposite. You need imperfection. You need regions of such immense density, such catastrophic overpressure, that they could overcome the explosive outward force of the Big Bang itself. These tiny patches of the early cosmos would have been so dense that light energy and space itself could not escape collapsing under their own phenomenal gravity to form a singularity. A primordial black hole, therefore, is not just an object. It is a fossilized remnant of chaos. It is a preserved piece of the universe's violent, turbulent infancy. Finding one would be like discovering a dinosaur embryo perfectly preserved from the moment of its turbulent formation. It would provide us with a direct physical probe into the physics of the first second of existence, an era so extreme that our particle accelerators can never hope to replicate its conditions. It's a period from which no light can ever reach us, forever shrouded behind the opaque plasma of the early universe. But gravity is different. Gravity is the ultimate narrator. It travels unimpeded from the moment of creation, and these black holes would be its messengers, carrying the story of their own cataclysmic birth across 13.8 billion years. They are the universe's oldest ghosts, and if we can finally see them, they will tell us tales of an epoch we once thought was lost to us forever. And the story they might tell extends far beyond their own creation. Consider the most profound enigma in modern cosmology: dark matter. For nearly a century, we have been haunted by its presence, an invisible substance whose gravitational influence sculpts the galaxies and choreographs the cosmic ballet. We see its effects everywhere, in the spinning of spiral arms, in the paths of light bent around galactic clusters, and in the very structure of the cosmic web. Yet its identity remains a complete mystery. We have spent billions of dollars and countless hours building ever more sensitive detectors deep in subterranean labs, hoping to catch a fleeting glimpse of an exotic, weakly interacting massive particle, a WIMP. We have searched for a new physics, a shadow world of particles interacting with our own, only through the gentlest of gravitational nudges. But after decades of searching, our detectors have remained silent. The shadow world has refused to reveal itself, and all this time a stunningly simple and elegant solution may have been hiding in plain sight, a solution that requires no new particles, no new forces, no physics beyond what we already know. What if dark matter is not some exotic, undiscovered particle at all? What if it is simply a vast, silent population of primordial black holes, forged in that first chaotic second of the Big Bang? It's a breathtaking proposition. The universe in its very first moments could have created the solution to its own greatest mystery. The very seeds of structure could be one and the same as the invisible matter that holds those structures together. Imagine it, the dark matter, holding our own Milky Way in its gravitational embrace, might not be a cloud of ethereal, ghost-like particles, but a swarm of trillions upon trillions of ancient black holes, each perhaps no more massive than an asteroid or as heavy as a small star. They would be completely dark, interacting with our world only through their collective gravity. They would perfectly mimic the behaviour we attribute to dark matter, all without requiring us to invent a single new entry in the standard model of particle physics. It is a theory of profound economy, a cosmic Occam's razor. It suggests that the answer to one of the universe's deepest puzzles isn't hidden in some exotic new realm of physics, but in the known, accepted, and terrifyingly powerful physics of gravity, pushed to its absolute limit in the crucible of creation. Confirming this would represent one of the greatest paradigm shifts in scientific history, recontextualizing nearly a century of astronomical observation. The darkness would finally be given a name and a face. But the implications of their existence spiral even deeper, reaching into the very architecture of the cosmos. One of the nagging puzzles in cosmology is the question of structure. How did the vast, majestic galaxies we see today form so quickly in the early universe? Our models, based on the gentle density fluctuations seen in the cosmic microwave background, struggle to explain the presence of supermassive black holes and fully formed galaxies just a few 100 million years after the Big Bang. It's a timing problem. There simply doesn't seem to have been enough time for gravity acting on tiny ripples of matter to pull everything together into the cosmic behemoths we observe. It's like trying to build a skyscraper in a single afternoon, with only a handful of bricks. Primordial black holes offer a stunningly effective solution. If they were formed in that first second, they would have begun acting as gravitational seeds, long before the first atoms even formed. While the rest of the universe was a hot ionized soup of plasma, these black holes would have been quietly, patiently accumulating matter around them. They would be the cosmic anchors, the primordial scaffolding upon which the first stars and galaxies could later condense. Instead of needing to build a skyscraper from scattered bricks, the universe would have been gifted a set of prefabricated super-dense foundations. The supermassive black holes we see at the heart of nearly every galaxy, including our own Sagittarius A, may not have grown over billions of years from collapsed stars. They could be the direct descendants of truly massive primordial black holes, ancient celestial monarchs that were born large and simply grew larger, their immense gravity corralling the gas and dust that would become the galaxies we call home. In this scenario, we are not just living in a galaxy held together by ancient black holes. We are living in a galaxy that exists because of them. They are not just a component of the cosmic web, they are its architects. This idea transforms them from passive relics into the active drivers of cosmic evolution. It connects the physics of the first microsecond to the grand tapestry of galaxies stretching across billions of light years. It provides a causal link written in gravity between the quantum chaos of the beginning and the magnificent structured cosmos of today. To find a primordial black hole would be to find the blueprint for our own cosmic home, a direct link in the chain of causality that leads from the Big Bang to the planet you are standing on right now. It is a story of cosmic ancestry, and they are our oldest, most enigmatic relatives. Reflecting on this incredible journey, we see that the quest for primordial black holes is more than a scientific investigation. It is a testament to the relentless, stubborn, and beautiful nature of human curiosity. It encapsulates the very essence of the scientific method, the formulation of a bold hypothesis, the decades-long struggle against the limits of technology, the patient gathering of null results, and the unwavering belief that with enough ingenuity nature's deepest secrets can be unlocked. This is a story driven not by the certainty of discovery, but by the tantalizing possibility that a profound truth lies just beyond our grasp. It is a multi-generational effort passed down from one group of scientists to the next, each generation building upon the work of the last, refining the theories, and designing ever more powerful experiments. This persistence reveals something fundamental about us. We are a species that looks into the darkness and is not satisfied with ignorance. We build instruments of breathtaking complexity, not just for practical purposes, but to answer the most fundamental questions of all. Where did all of this come from? What are the rules that govern existence, and what is our place within this vast and often baffling cosmic drama? The search for these tiny invisible objects is a manifestation of our deepest impulse to understand our origins. It connects us to the earliest stargazers who charted the heavens, to the philosophers who debated the nature of the void, and to every child who has ever looked up at the night sky and felt a sense of overwhelming awe. We search for them because we must, because to be human is to be a seeker of knowledge, to push against the boundaries of the unknown, and to try and read the story that the universe has written for us. And so we look to the horizon to a future that promises to be more revelatory than any time in human history. We are on the verge of deploying a new generation of cosmic observatories that will perceive the universe in ways that were once the stuff of science fiction. The Laser Interferometer Space Antenna LISA will unfurl its millions of kilometers of laser arms in the silent vacuum of space, listening for the slow, gentle gravitational murmurs of merging primordial black holes, a frequency utterly inaudible to our ground-based detectors. The Einstein Telescope and Cosmic Explorer will create a global network of subterranean gravitational observatories, an order of magnitude more sensitive than anything that has come before, capable of detecting the faintest space-time tremors from the edge of the observable universe. The Nancy Grace Roman Space Telescope, with its panoramic eye, will conduct the largest ever survey for microlensing events, potentially spotting thousands of these dark wanderers as they drift through our galaxy. These are not just telescopes. They are time machines. They are our proxies, our extended senses designed to reach across the unfathomable abyss of cosmic history and deliver a message from the beginning. One day, perhaps soon, an alert will flash across computer screens around the world. An algorithm will flag a signal, a unique gravitational wave chirp, or a peculiar pattern of lensing that bears the unmistakable signature of a primordial black hole merger. In that moment, everything will change. The ghost will become real. The speculation will become fact. Humanity will for the first time hold in its hands a tangible piece of the universe from before the first star ever ignited, before the first galaxy took shape, from the very first fiery moments of existence itself. That discovery will not be an end, but a beginning. It will open up an entirely new field of science, primordial cosmology. We will be able to study the mass distribution of these objects, which in turn will tell us about the precise conditions of the Big Bang, mapping the landscape of the early universe with unprecedented clarity. They will become our ultimate tool for understanding the birth of space-time, a Rosetta Stone for deciphering the language of creation. They are the missing link in our cosmic story, the keepers of the universe's oldest secrets. The quest continues, fueled by the conviction that hidden within the deepest darkness are the most profound revelations. We will keep listening, keep searching, and keep looking up, for we know that the answers to who we are and where we came from are waiting for us out there in the silent, patient, and primordial dark.